instruct accordingly. And let's roll. Right, good morning, and let me welcome all of you to this webinar, the CARIBSAN webinar. It's the first in the series with CAWASA, and we are pleased to be able to collaborate with the water offices of France and Martinique. This is the final in our series of webinars for 2021. The Caribbean Sanitation Nature CARIBSAN project was launched on the 27th of September 2021. This project is a partnership among the water offices of Martinique and Guadeloupe, the ODE, the International Water Office of France, the WASCO, that is the Dominica Water and Sewage Company, WASCO in St. Lucia, the INRH of Cuba, and CAWASA in the implementation of the CARIBSAN project during the period June 2021 to December 2022. The project is financed through the Interreg program of the European Union, the Agence Française de Développement, the Martinique Water Office, the Guadeloupe Water Office, and the in-kind contributions of the other partners. This planted filter technology that is constructed wetland is a nature-based solution that was developed for the treatment of wastewater in tropical areas. The project aims to promote the development of this technology in new pilot areas, drawing from the experiences of Martinique with a view to setting up the system in the wider Caribbean region. It is expected that the project will give the participating water utilities the opportunity to explore alternative technologies for wastewater treatment as a pilot, which will give the staff of the operators in the water utilities an opportunity to explore alternative technologies in wastewater treatment as a pilot, which will give the staff in the wastewater departments exposure to the emerging softer technologies, as well as the potential for expansion on a larger scale in small coastal communities with sewage discharge challenges. So we are very pleased to be associated with this project as CAWASA, representing our water utilities, and to partner with the International Water Offices of France and the Water Office of Martinique. This morning, we also have with us several members of I don't know how much time we will have because we have over 26 people subscribed to this session this morning. So we wouldn't have time to go around the table to introduce everyone, but we have the people from the International Water Office in the persons of Camille, Madec, who is responsible for communications on the project, Mr. Joseph Pronost, Pascal Molle, Virginie Clermy, who is at has project coordination oversight, Philip Segun, and I think there are some others who have joined. I don't remember all the names here. And we have Mrs. Ivana the Costa James of the WASCO. She's the Chief Operations Manager at the WASCO in Dominica. And I think we have from St. Lucia, I'm not sure if Mr. Regis is on from WASCO, the General Manager of WASCO. I think Mr. Etenoff promised to join briefly because he has also another meeting this morning. So I'd like to welcome all of you. I also know that we have some participants from Barbados and Trinidad and Tobago, and I think there's somebody from some of the other islands who also registered for the session this morning. So I'm going to hand over to you, Camille.
Thank you, Ignatius. I think that our colleague Pascal will share the screen, and we will give the floor to Philippe from the International Office for Water to have a quick description of the CARIBSAN project, and then give the floor to the two experts, Pascal Molle and Joseph Pronost, who will hold the presentation.
Thank you. Thank you, Camille. Good morning, dear ladies and gentlemen. I am Philippe Seguin from the International Office for Water, and I am very happy to say a few words on behalf of the CARIBSAN project. During this first cooperation with CAWASA, the CARIBSAN project aims to develop the treatment wetlands in the Caribbean for the wastewater management. 3 ways to address this goal: preliminary studies for the treatment wetlands implementation in pilot zones, concerning choice of plants, development of methodology, etc., capacity building, and third ways is communication and dissemination of the results in order to strengthen a Caribbean cooperation between actors in sanitation. CARIBSAN concerns 5 islands for this phase, for this first phase: Cuba, Dominica, St. Lucia, and the French West Indies, Guadeloupe and Martinique, and CARIBSAN gathers 9 partners. CARIBSAN must be finished on the 31st December of 2022, as Mr. Jean said. This deadline is very close regarding all the activities we have to do. If we have good results, I hope we will have good results. I'm sure we will have good results. The next phase is foreseen to build the treatment wetlands. This webinar is the first of a collection to share experiences between other partners. There will be other webinars in English or in Spanish, as well in French. And now I am very proud to welcome Mr. Pascal Molle and Mr. Joseph Pronost for this webinar. They are the high-level experts of treatment wetlands in France. We are lucky. Dear colleagues, you have the floor. Thank you very much.
Sorry, I just had to make escape to the presentation to be able to put on my micro. So I am Pascal Molle, research director in INRAE, which is a public research institute in France. And I will share the presentation with Joseph, the technical part of the presentation. So we already had the introduction to the CARIBSAN project. And then the objectives of this webinar is to give you some first general introduction about treatment wetlands, different kind of technologies, and for which application we can use them. And after, Joseph will present the main mechanisms involved in treatment wetlands. I will come back on the adaptation of treatment wetland for domestic wastewater in tropical climates. Big work we did in the French tropical islands. And Joseph will finish with advantage and drawbacks about treatment wetlands. And we will have a 30-minute question at the end. So general introduction about treatment wetlands technologies. So the first is, what is a treatment wetland? It's an engineering wetland system. That means it's not a natural wetland, which is designed to harness natural processes for the purpose of improving water quality. So the other key word in the sentence, it's improving water quality. There is an objective for treatment. It is technically and operationally simple, but it involves complex interaction between water, soil, plant, microorganisms, and the atmosphere. During this webinar, we will not go too deep in the mechanisms involved, but if you are interested in and the different kind of application, there is a free book which is available on the internet, which is dedicated for treatment wetlands, with some designs example application. So please feel free to download it and read the documents. Basically, when we are talking about treatment wetlands or constructed wetlands, that's the same term for the same technologies. That means we are focusing about treatment, as I said, and we have two kind of main technologies, what we call surface flow wetlands, which are basically pond system with plants, and subsurface flow. And in subsurface flow, we use porous media in which the water will flow. That means there is no ponding water or no flowing water on the surface. The water flow inside a porous media. We make differentiation according to how the water goes through the system when we are talking about subsurface flow wetlands. Whether the water flow horizontally into the system or vertically. And then, according to the flow, we can have systems that are fully saturated or not. And we can have flows that go downflow, upflow, or mixed, sometimes down, sometimes upflow. There is a lot of different kind of implementation and design, and you can see that if you go through the bottom of the scheme, there is a lot of technologies. So that was a first terminology that was made something like 10 years ago, and it evolved a little bit. Just to give you an idea about the number of treatment wetland systems that can exist. Basically, we have two. The main system are horizontal flow, the one on the left, which is subsurface flow. Yeah, there is no question. No, okay. So on the left, yeah, someone has his microphone on, and I got some echoes. I don't know who is it. If you can, please, for the moment, put off your micro. Thank you. So on the left, you have what we call a subsurface flow treatment wetland. That means there is a porous media in which the water flow horizontally within the system, and we saturated the system thanks to a pipe that allows to adjust the level of water below the surface of the system. On the right, you have what we call a vertical flow system, and this system is fully drained at the bottom. And when we apply water at the top of the system, the water flows vertically by gravity, and the system is not saturated. For the vertical flow system, we can whether apply raw wastewater without any pre-treatment, that means treating the sludge and the water at the same time, or use vertical system with different design to treat pre-treated wastewater. And there is as well different evolution of the system, trying to mix both of the main configuration I just presented, horizontal flow and vertical flow. Here you have a scheme of a vertical flow system, which is fed on the top. The first part of the system is unsaturated, so we are promoting aerobic activity, and below there is a vertical flow saturated system. In this system, we try to implement two zones in which we will be able to develop different biological activity. Another development that has been done since a decade, it's trying to intensify a little bit the treatment wetland system. And so here you can see two examples of vertical flow and horizontal flow system saturated with forced aeration. That means we use mechanically we blow air mechanically within the system to improve oxygen transfer. Basically, just a few rules to have in mind is that when we want to design such kind of system, we need to adapt the surface and the media we use within the wetland system. And so for unsaturated system, we use classical surface loads. So that means how much of water per square meter we can put per day, or how much of gram of pollutant per square meter we can put per day to reach a certain level of removal performances. When we are using saturated treatment wetland, we use simplified models coming from chemical engineering to fit the retention time into the system. There is one thing we need to be aware of, is to avoid any clogging of the media with time. And so there is as well some rules that we will start discussing later to manage the clogging and to be sure that the system can operate over a long time perfectly. As well, the adaptation to the climate is important, because biological activity will depend strongly from temperature. And so we have as well some rules to adapt the design of the systems according to climate. We will come back on it later. So I just explained the different kind of system, but you have to know that as well that we can use different combination of treatment wetland system in series. So here you have an example with 2 stages of vertical flow system, and you will understand better later, but you can see here that there is different cells on the first stage and as well on the second stage. So you can see that we can mix different kind of system. Here as well, you have another example mixing vertical flow system, horizontal flow system, and surface flow system. It's just to give you an idea that the number of treatment chain that we can do with the wetland system is huge. And so we have to adapt the design and which system we want to use according to the local context and the target for the outlet. That means which level of performances we want for which application after, if we want to reuse wastewater, treated wastewater, or if we just want to discharge into the water body. As well, we can use recirculation between stages, or use specific materials as porous media to promote some specific chemical reactions. So it was an overview of treatment wetland family. I just would like to present some different kind of application now. So what is interesting us actually is the application for domestic wastewater, and we can use such system from household scale. That means having a treatment wetland in a house garden to treat the wastewater from the house. But we can also use treatment wetland to treat domestic wastewater from communities and until big communities. The biggest treatment wetlands actually in the world treating domestic wastewater from a community is for more than 25,000 people equivalent. And another important thing is that you can adapt as well the shape of the design to try to reach aesthetic aspect, as you can see here on the treatment wetlands in Thailand. Another application, possible application, is to use treatment wetlands to treat sludge. That could be sludge from activated sludge. Here on the left, you have a picture from a activated sludge treatment system in Denmark, a big one. And on the background of the picture, you can see the treatment wetlands are are designed to treat the exit sludge from the treatment plant. But you can use as well treatment wetland to treat septage. That means when you have sludge coming from septic tank, you can treat them on treatment wetland as well. So design will be different, operation will be different than treating domestic wastewater, but you can achieve good performances. And here is just a picture during a construction of adaptation of the sludge treatment system for tropical climate. Here it was in Molle, Iceland, for 5,000 PE. Another possible application is to treat the overflow of combined sewer. When you have big events, you can have combined sewer that overflow with a mix of rainwater and domestic wastewater that can impact the water body or the environment. And you can treat locally this overflow with treatment wetland. So here you have a picture of a system in France treating 1,500 cubic meters a day when it's overflowing, of course. And which is important is that we can ensure a specific outlet level in terms of concentration, pollutant concentrations. Another application is for industrial or agro-food industries. So just to show you that it's possible to treat agro-food industry because it's easily biodegradable. And here on the left, you have a picture of treatment wetland treating rum distillery effluent in Martinique, Iceland, 250 cubic meters per day during production days. And on the right, in USA, it's an application to show you that it is possible for specific compounds to treat as well effluent from chemical industry, here for methanol and benzene. The last point I would like to present you is that we can design the system for different purposes. And here you have an example of a treatment wetlands close to a building. It's a library, university library in US. And here they treat the effluent coming from this library, including toilets, and to be able to reach outlet level of water that is in accordance to the reuse of the treated wastewater for toilet flushing. So there is 2 points that are interesting in this picture is that we can reach reuse purposes with such system, and as well we can introduce the wetland system into the urban aesthetic. That means trying to change the configuration of the cities and trying to bring back green areas in the cities. I will let the floor to Joseph to present the mechanisms involved in treatment wetland system. So Joseph, the floor is yours.
Thank you, Pascal. I hope that you hear me quite well. Okay. Yes.
Yeah.
Thank you. So my name is Joseph Pronost, and I am the training director at International Office for Water, but also I am an expert related to wastewater treatment. So I will present you a little part of this global presentation about the mechanisms involved in constructed wetlands for wastewater treatment. Next slide, Pascal. So here you have a scheme view about a classical wastewater treatment plant in metropolitan France, that is to say for mild climate, that we realize in the part of France that it is included in Europe, of course. And so you see from the left to the right, at first we have the inlet of the wastewater treatment plant, and after a screening and simple screening device, and after the counting and sampling of the wastewater, this raw wastewater will go inside the flushing tank. The aim of this flushing tank is to have a sudden flow rate on a big volume which will go on the filters. So this is some constructed filters And there is a first stage, usually in metropolitan France, and first stage with usually 3 filters in parallel. And by this way, we will feed one filter during 3.5 days, and the other 2 filters will have a sort of resting period during 1 week. And after we'll recover the filter, the treated water from the bottom of the filter. It will go inside a second flushing tank in the aim to supply the second stage of filters. And usually we have at the second stage 2 filters in parallel. Of course, you notice, according to this picture, that mainly we use some vertical filters in this type of technology. It's important to notice that this type of treatment is the main built treatment, wastewater treatment plant in metropolitan France. It's possible to say that roughly 2/3 of the wastewater treatment plant built in France for a capacity less than 1,000, 2,000 population equivalent. This is this type of treatment. So this is a big success since several years. Next slide, Pascal, thank you. So as Pascal did explain to you before, we use usually some vertical filters. And so you have on the top of the filters the inlet through some pipes. And after you will go through a filter whose depth is roughly 80 centimeters. This is usually some non-saturated filters, and at the bottom you have some drainage pipe, and some pipes for aeration are connected as the same of the drainage pipes. Through this aeration system and through the sand itself between 2 batches, there is some air incoming, and then we have a sort of guarantee to obtain an aerobic treatment. You have some global values about the granulometry, about the grades of the material that we install inside this type of filters. At first, you have a filtration layer whose grade is between 2 to 6 millimeters. And just under this filtration layer, there is a transition layer. Usually the grade is between 5 to 20 millimeters. And at the bottom, there is a drainage layer. And the granulometry is between 20 to 60 millimeters. All these filters are watertight, and that's why that there is one geomembrane for watertightness. Thank you. Next slide. About the mechanism, you have to understand that phenomena are very complex. In orange color, you see this phenomenon, these mechanisms. So there is some hydrodynamic phenomenon, some biological activity, some plant activity, and some gas transfer phenomenon. Yes, you could click. Yes, thank you, Pascal. Then it is very important to obtain an equilibrium between these processes. Otherwise, if there is too much biological activities in comparison with the porosity, for example, you may have some malfunctions. So this notion of equilibrium is very important. It's necessary to adapt the design to some external factors, such as the climate. For example, for tropical areas, you have to take into account, of course, the temperature. The operation tasks on the constructed wetlands management is important. Of course, these operation tasks are not complex, but it's very, very important to ensure them in the aim to ensure this good equilibrium. So there is some complex phenomenon on interaction. And because this is a complex type of treatment, there is a lot of points to check during the design. So this type of treatment seems to be very simple, but in fact, it is complex according to the design. You have many points to check in the aim to ensure the good reliability of the treatment. Next slide, Pascal, thank you. So there is, you see on this picture, this the evolution of the vegetal growing. So this is a typical configuration in France, in metropolitan France, in Europe. So you see on the first pictures, the first stages of, the first stage of filters, of the 3 filters. So you see the feeding points at the surface of the fine gravels. And on the second plan view, you discover also the second stage of filters. During the first year, you have a little growing of vegetal. In metropolitan France, we use usually some reeds, quite always some reeds. And during the first year, you obtain the growing of these reeds, but you have to take care especially about the growing of weeds, and you have to clear the filters from these weeds. And after several years, you obtain the aspects of these filters of the last picture. So you see that the development of the reeds is very good. And the height of these reeds may reach, for example, 2 meters height. Next filter, next, yes. So through this specific technology of constructed filters, constructed wetlands, it's very important to have a batch feeding mode. Also, during some times of the day, we feed the filters. If you could click, Pascal, thank you. And then the feeding phases, you will feed the filters with a high flow rate in the aim to obtain a good repartition by submersion and with a big volume too. And because you obtain a good submersion, you improve well the retention time and you develop a good active surface, a good active, horizontal active surface. During these phases of feeding, you obtain the biofilm development, and then the bacteria will be very active on these gravels and sands. And during some other periods of the day, there is some unfeeding phases. That is to say that you store the raw wastewater at the inlet of the filter in the batch tanks. And during these phases, during these unfeeding phases, the air will come between the sand grains, between the gravel grains also, and then you will obtain an aeration phenomenon. So we insist that our design is very based about the aerobic phenomenon, usually as the first priority, but it may be complete by some other possibility you will see after. Next slide, Pascal. Here you have some views of some typical feeding by batches. So usually we use some siphon. By this way, there is no need to have some energy. And then if you have some enough slope, you will obtain a treatment without energy consumption. But it's possible if the slope of the ground is not enough to use some pumping station and to realize some batches by pumps. Next slide, thank you. So as a resume, the key points of the treatment, this is generally, this is vertical flows, mainly vertical flows. There is the feeding by batches in the aim to obtain some homogeneous water distribution at the surface. Between 2 batches, there is so some oxygen transfer. We obtain some submersion, few centimeter, 1, 2, 3, 5 maximum centimeter at each batch. This is some aerobic treatment. We have at the inlet some screen raw effluent, and there is no primary treatments. And we use some specific material with some very precise characteristic of permeability, granularity, and so on, such as gravels and sands. The filters are in parallel, and we have then the alternating periods of feeding, 3.5 days, and resting, 3.5 to 7 days. And this organization helps us to prevent the clogging of the filters. Next slide. So about the treatment processes, we have some filtration processes, especially at the surface in the 5 to 10 first centimeters of the filter, but even we have some filtration in the depth also. On the biofilm, which is mainly positive, we will absorb some negative pollution, such as organic matter, BOD5, COD, for example. And after adsorption, we'll obtain the assimilation by the bacteria, aerobic assimilation. According to the design, it is possible to implement some nitrification, and especially if you have some filters organized in 2 stages. Eventually, it's possible to obtain some denitrification processes, also on some dephosphatation. If you could click, Pascal, thank you. And about the design, we have to take care about the clogging risk at the surface and the clogging risk in depth. And we have to take care also in the aim to have a good efficiency, to take care to have enough oxygen inside the filter. Next slide, thank you. On this table, this is a resume of all the mechanism in the first column that you see. On the second column, this is the active media, which is mainly responsible of this mechanism. And on the third column, you have the removed parameters by these mechanisms. As said before, the fine gravels on the coarse sand will ensure the filtration process. By this way, you will remove the suspended solid. The biofilm and the bacteria, they will ensure the adsorption, and you will adsorb some fine suspended solid, BOD5, COD, ammonium, and especially the particular, the BOD5 and the COD in fine suspended solid. But the biofilm on the bacteria will ensure the aerobic assimilation in the aim to remove quite very well the BOD5, the COD, and a part of the nitrogen and the phosphorus. If you have 2 stages in series, it's possible to obtain a good nitrification in the aim to remove the jaldal nitrogen and the ammonium, because the ammonium is included inside the jaldal nitrogen. And if you create some anoxia zone, for example, some saturated zone, and if there is enough organic carbon inside this anoxia zone, it's possible to obtain some denitrification phenomenon in the aim to remove the nitrates. If you add some specific material, reactive material, or if you add some coagulant, such as ferric chloride, you could obtain some dephosphatation in the aim to remove the phosphates and the total phosphorus. You have to notice that the main role of the vegetal is not to remove the pollution parameters, but the main role of the vegetal is to maintain the permeability. In fact, of course, there is a little plant uptake of nutrients, a little assimilation of mineral nutrients, nitrogen and phosphorus, but this removal of nitrogen and phosphorus by vegetal, by plants, is very, very low, less than 1%. About the risk that I did mention before, we take care about this risk during the design. For example, about the clogging risk at the surface. So we design some extended treatment. Thus, the repartition of the inlet suspended solid load is done on a big surface, and then you decrease this clogging risk at the surface, because this is vertical flows that we use mainly. The main role of the vegetal, this is to maintain the permeability, because the vegetal stems will form some holes inside the sludge at the surface. By this way, they will ensure this role to maintain the permeability. In the aim to prevent the clogging risk in depth, it's important to design all the wastewater treatment plant with some resting period. For example, 1 week of resting period, of non-feeding period. And then during this resting period, we obtain a partial aerobic mineralization of the biofilm, and then we improve again the permeability in the aim to feed again with the wastewater, the filters. In the aim to prevent also the clogging, we don't use some very fine natural soil. It's suitable to use some fine gravels, of course sands, with a good granulometry. In the aim to prevent the lack of oxygen, that is to say the bad removal of organic matter and the bad removal of general nitrogen, it is suitable to fill these filters, these constructed wetlands by batches. Then we will have oxygen between two batches, and we have some filters in parallel. And during the resting period, the oxygen will come again inside the filters. So if the design is done according to these prevention rules, we obtain a good designs, a good robustness. This type of wastewater treatment plant is reliable. And for example, the lifespan of this type of wastewater treatment plant in France, it may be, for example, 35 years in metropolitan France. Next slide. So this is only a picture to show you the holes around the stems of the reeds in the aim to maintain the permeability at the surface. Next slide. So I did finish for this part of the presentation. Thank you very much. It's up to you, Pascal.
Thank you, Joseph. So I will go on presenting the adaptation of treatment wetland for tropical climates. And one of the first questions we had when we wanted to adapt the system was how to adapt the design, because thanks to the climate, we could promote higher biological activity. So the question was how to reduce the surface of the system. Is it by reducing the surface of each cells or the number of filters? Which material to use? Can we work without sand? Because sand is sometimes difficult to find locally. And so if we could implement system without using sand, only gravel, it would be really interesting for the tropical islands. And as well, there was a question about the volcanic material we can find in the islands, and so how are they suitable or not to be used, and which impact on treatment performances such material could produce. And of course, the other question was the question of plants, because the fragment australis that we use in France and mainly all Europe are not present in many of the tropical islands, or if present, considered as invasive plants. So it was not possible to use them, and there was the necessity to conduct a work as well on the choice of plants. So what we did for the adaptation of the number of filters, the idea was to work with a first vertical flow system that is able to treat raw sewage without any pre-treatment, to be able to manage sludge and treat wastewater, using only 2 filters in parallel, but not reducing the surface of each cells, comparing at what we do in temperate climates. The idea here was to maintain the robustness of the system to accept hydraulic overload, because of course in tropical climate there is a lot of rain. And so this interesting feature of hydraulic acceptance, overload acceptance, had to be maintained in tropical climate. So we decided to only choose 2 filters in parallel, because the number of filters in parallel is the main role of making alternation of feeding and resting period is to manage the clogging. And as temperature are higher in tropical climates, the biological activity is higher as well. And so we can mineralize more easily the organic deposits that we form at the surface. Then considering the choice of plants, what we did, we started from a selection of plants according to the characteristic we wanted, and looking at in the different literature or with discussion with local experts of tropical plants, which plant can be used or not. And then we selected 21 species to be tested in batch experiment to test their robustness to specific conditions like anaerobic, the anoxic stress when there is anaerobic condition too long and too high, or the water stress as well. And then we selected 8 species to be tested in different full-scale systems at different organic and hydraulic load. Thanks to that, we were able to define some different plants that could be used in tropical climate for wastewater treatment system. And here you have an example of 3 of them, like Heliconia psittacolum, Canna indica, and Cyperus alternifolius. So one of the interests is that when using, for example, Heliconia, we have interesting aesthetic aspect as well, thanks to the flowers. Concerning the different design and system we wanted to test it in tropical climates, we worked on 7 full-scale systems in different French overseas, and 4 treatment plants used a first vertical flow system, unsaturated. And here we tested different filtration layer depth and with or without recirculation to see, according to the design, which performances we could reach. On 3 other plants on the first stage, we tested the vertical flow system with the first layer unsaturated and the second layer saturated. The idea here was to see how we could improve the performances of the first stage to be able to work only with one stage and stay compact in terms of footprint. So here as well, we tested the depth of the different layers, the unsaturated and saturated layers, and with or without recirculation. And as well, on a specific plant, we use a second stage, which is a simple tracking filter, very simple one, to be able to finish nitrification and to improve total nitrogen removal while being compact as well, because the total surface of the filters and the tracking filter was below 1 square meter per PE. So thanks to that, we observed that the vertical flow system had similar performances than in temperate climate for COD, BOD, and TSS. It means quite good, but a better nitrification thanks to the climate. And it was possible to reach almost complete nitrification using only one stage with 80 centimeters of 2.6 millimeter gravel and recirculation. So here you have an example of the outlet quality in terms of concentration for COD, BOD, TSS, and gel nitrogen. And here it's for 0% of recirculation or less than, let's say, 100% or more than 100% of recirculation. And here you have, for the same conditions, the removal rates. So you can see that we can improve performances thanks to recirculation and reach very low level of gel nitrogen at the outlet. So if you are interested, there is a paper that can give you that present those results. Another interesting feature that we observed and that are interesting for tropical climate is the resilience and the reliability of the system. we tested two kind of shocks, let's say, on the system. One is a lack of maintenance, and we tested a system without any alternation between feeding and resting period during 6 months. So that was on purpose that we we did that. And the other, which is feature that is observable on this graph, is that the acceptance of hydraulic load. So here you have a cumulative frequency of the hydraulic load applied on different system in blue, orange, and green. And the red line is the nominal capacity in terms of hydraulic load. And the gray line, vertical gray line here, it's the hydraulic load on which in temperate climate we observe that we start to have a decrease of nitrification performances. And what we observed here is that we were able to run system like the system in green with almost all the hydraulic load over the nominal load we usually use until specific events with more than 2.7 meters a day on the filter in operation. That means something like 7 to 8 times the dry nominal flow. And it's just to show you how it is possible to accept very big tropical climate events in terms of rains without disturbing the system, neither in terms of performances. Thanks to all this monitoring that we did during many years on the different system, we are able to propose different design according to specific constraints. So if we want to work with or without electricity, if we have combined sewer or not, what are the limits in terms of load? If we have intermittent activities, that let's say in case of a touristic area in which you have a huge variation of load, and you have the footprint and the minimum and concentration we can respect. So that guarantee is not the average here in terms of performances or outlet concentration for each parameters. The last column is whether we can put UV disinfection at the end to reach a quality that is able to promote reuse or just discharge in bathing area. What we observe that we can have a compact system that can reach classical, not very stringent, but classical performances we expect from system. But we can go deeper with more stages, sometimes increasing the footprints and going until high performances, quite interesting performances as well for total nitrogen removal if it's targeted. The other observation we did is that we compare the system to classical treatment system. And so here I will present you some percentile values of outlet concentrations and after as well performances. And so here you have a curve with different systems that has been monitored for activated sludge, rotating biological contactor, pond system in blue, and vertical flow through wetlands. And for example, if I want to respect 35 milligram per liter of BUD at the outlet, I can go to which the line of each process of each technology I want to select. And for example, for activated sludge and rotating biological contactor, I can see that I will respect this value in 75%, a little bit less of the time. And if I go to to the vertical flow system, for the same value, it will be about 93% of the time. So it allows to compare the different technologies in terms of robustness in tropical conditions. And what we can see for BUD, CUD, TSS, nitrification, that pond systems are always better than activated sludge and rotating biological contactor. Let's say I want to express that this survey has been done for treatment systems that are below 2000 PE. Of course, when you have big activated sludge, there is always people maintaining the system, and you can better control the performances. But for small size, let's say below 2000 PE, it's what we observed here, that finally pond systems are more resilient and more robust than activated sludge and rotating biological contactor, mainly because for activated sludge, each time there is a storm event, you have some losses of sludge. And this will impact COD and TSS at the outlet, of course, but as well, a loss of sludge means that you need to recover again nitrophene bacteria over time to recover the nitrification performances as well. And so we observe that it affects the nitrification as well. For rotating biological contactors, the main issue is the separation as well, which is sensitive to storm event, separation of sludge and treated wastewater. Just to show you that there is as well a guideline that we did for the adaptation of treatment wetlands in tropical climates that you can find freely on ResearchGate. And so do not hesitate to go there and download it. And as well here, it's on the right, it's a picture of a treatment system in Martinique Islands. So you have new buildings that has been done, and close here on the right, on the bottom right, you have the treatment system for all these buildings. You can see that it's quite compact finally, and well integrated into the landscape. Joseph, I give you back the floor. Your micro is
yes. Thank you, Pascal. So I will present you the advantages and the drawbacks of constructed wetlands according to the type of configurations that we did present to you before. So the first drawback of constructed wetlands in general point of view, this is a required surface for an extended treatment. So this required surface is quite high, but as Pascal did explain to you, it is possible to imagine some more compact unit with a used surface of filter equal or less than 1 meter square per population equivalent. After the second disadvantage or drawback of this type of system, this is the annual cutting of vegetal, and you need to remove this vegetal from the filters. And especially this is a big drawback if you have some high surface of filters of constructed wetlands. Especially during the first years, you have to remove the weeds. And of course, if you have a big surface of constructed wetlands, this is a big work. And there is some weeds proliferation if you are in the case of too low hydraulic load. If you want to build a system without any energy, you need a natural slope of the ground, and this slope needs to be high enough. Sometimes there is some risk of undesirable fauna, such like snakes, for example, which may be a little problem if you need to cut annually this vegetal. So you have to take care, in fact. Before to build this type of treatments that we did present to you, you have to check the availability of the fine gravels, of the coarse and fine sands. And if these type of material are not so much available, it's often necessary to adapt the design in tropical area, and especially in tropical islands. The investment cost of this type of constructed wetlands that we did present to you has a high investment cost, and especially when the wastewater treatment plant capacity is high. That is to say, when the wastewater treatment capacity is high, this type of treatment is less competitive in comparison with activated sludge if you take care about the investment cost. On the cost of the activated sludge process, usually the investment cost for activated sludge process is lower for high capacity of wastewater treatment plant. Of course, you need to find some available endemic vegetal on local adapted material, as said before. And then this is also a constraint. You have to take care to find the good adapted endemic vegetal. Next slide. But there is, of course, many advantages of this type of constructed wetlands. At first, the good removal of suspended solid. So it's easy to reach some suspended solid content less than 15 to 50 milligrams per liter, according to the type of design that you will implement. We have a good removal of organic matter too. The BOD5 is oftenly less than 25 milligrams per liter, and the COD content may be less than 75 to 125 milligrams per liter. According to the efficiency, according to the quality of treated wastewater, it's possible to obtain some nitrification, and thus you will reach some gel-dial nitrogen content less than 6 or less than 40, according to the type of design that you will implement. It's possible to have a partial denitrification with a total nitrogen less than 35 milligrams per liter at the outlet. And you could have also the phosphatation with a phosphorus content less than 2 milligrams of phosphorus per liter. We are able, with the type of constructed wetlands that we did present to you, to treat some raw wastewater. And in this configuration, there is no primary treatment, which is required. And this is a very good advantage because thus there is no primary sludge production. And you know quite sure that this primary sludge is often a problem because there is some problems of odors, and you need to extract this primary sludge from the wastewater treatment plant quite regularly. Because there is no primary treatment and because the sludge will stay a very long time on the surface of the vertical filters, you obtain a minimal sludge management, and then the extraction of the sludge from the wastewater treatment plant will be done every 15 to 20 years or more. During this long period of non-extraction, you obtain the decreasing of the sludge production because there is a very big and long phenomenon of mineralization of the sludge, of the organic part of the sludge. And of course, this sludge, especially if it is sludge from municipal wastewater, it is possible to reuse this sludge in agriculture. This type of constructed wetlands is easy to operate. You have to ensure the rotation of the filters 1 to 2 times per week. You have to remove the weeds during the first years, and you have to ensure the annual cutting of vegetals. You have well understood that there is none or few electromechanical equipment, and then the electromechanical maintenance is very reduced at the minimum. Next slide, Pascal, thank you. As there is the possibility to have some wastewater treatment plant without without electromechanical device, then the energy consumption will be equal to 0 or will be very low in comparison with some other processes. As Pascal did explain to you before, it's possible to accept some very high hydraulic loads, but even some high organic loads variation. And of course, this is often the case of little wastewater treatment plants. This is also a good advantage that this type of wetlands is included inside the nature-based solution. We are now able to find some endemic vegetal for tropical climate. So we have the solution about the type of vegetal which will be well adapted. As Pascal did present to you, it's possible to treat some other type of wastewater, agricultural, industrial, rainy wastewater, but even the sludge. I did discuss about you as a drawback about the high investment cost when the size of the wastewater treatment plant is high, but in fact, when the size of the wastewater treatment plant is low, then we will obtain for this type of treatment some lower investment costs in comparison to other treatment, and especially in comparison to activated sludge process. And in all cases, low or high capacity of wastewater treatment plant, the operation costs are lower. Next slide, but I think it's up to the questions and answer. Thank you very much for your attention to these presentations. Thank you.
Right. I think, thank you very much for these interesting presentations. We already have a few questions in the chat room. I don't know if you want me to call them out. The first question is, what is the reason for the annual cutting or of the vegetation if the plants are part of the wetland? And then do we need to replant them? Is it pruning or is it trimming?
Okay, so we harvest the plant because in the cycle of vegetation of any plants, there is a growing and period, and after there is a dying season. And so we remove the plant annually. Well, it can change a little bit according to the plant we use, but it's basically annually because we do not want to let this vegetation die and fall onto the surface. That will increase the organic deposit on the system. And so we prefer to remove it, and there is no need to replant because we select plants that grow from the rhizomes. And so it grows itself without replanting.
Yeah, these plants, the birds of paradise as we know it, that's the heliconias. They are a rhizome, so they reproduce easily in the wet areas. And the next question. Yes,
please,
sorry.
Ignatius, yes. And if you leave the plant all the years on the surface of the filter, so they will die, as Pascal did explain, they will decay, so they will increase the organic load, but especially they will reach the sludge production. So if you leave all the vegetal, you increase the sludge production and you decrease the frequency of the sludge extraction, in fact, which is a very big operation task.
Yeah, the next question is it asks, are the constructed wetlands effective for oil and grease removal and microplastics?
Well, if you, for oil and grease, if you are talking about what is coming from the kitchen or restaurants activity, there is no problem for that. If you are talking about oils that can come from runoff on the road, and that goes into the sewer and then the treatment plant. It's small concentration as well, so there is no issue in terms of impact on the performances of the system. But basically there is some what you say pH compound that are linked to solids and that will be stored on the system, on the deposit organic on the organic deposit on the system. But the ones that are not linked to solid and will pass through the system quite like in every treatment system. And so the part that will be stored on the organic deposits, as we store the sludge during years and decades, we observe that we can degrade this pH aromatic hydrocarbons. If you are talking about treating petroleum industry, that's another topic, because the concentration of hydrocarbons are very high, and so we cannot design the wetland on the same way. It exists system in the world that treats effluent from petroleum industry, but they are very different from the technology we presented today.
There's another
and for
part.
yes, for microplastics, there is a few studies that come up now since this topic has become a hot topic. And what we observed is that we have more or less the same performances on microplastic than on TSS. So as we have good filtration performances on this system, we observed on the few studies that has been done until now, we observed that the performances on microplastic is over 80%.
Yeah, there was another part to the question. What about the effectiveness or the performance during the dry or the wet seasons as experienced in the Caribbean?
Yeah, that's a good question. Well, the fact is that we try to adapt the design according to the worst period. So in the dry season, we can expect to have only domestic wastewater and no water coming from the ground, for example, or rain events. And so in that case, if the load during the drying season, the rainy season is not too high comparing to the dry season, we can manage a design that will accept, let's say, the double hydraulic load without any issues. That means we know that we can double the hydraulic load during rainy seasons. But if the difference of hydraulic load is more than the double during rainy and dry seasons, we need to adapt the surface. And in this case, during dry season, the hydraulic load will be lower. If it's too low, we can have an issue in terms of water stress for the plants, but not for the performances of the system. And if we have too much water stress, the problem will be the competition with weeds. And in that case, we can adapt the design with a saturation layer at the bottom to be sure that we will have enough water that plants can use, or we can implement recirculation during dry seasons, but that means needs of electricity. So there is adaptation, possible adaptation. There is a robustness of the system, and if the difference are in terms of hydraulic load are too high, we can adapt the design to face this issue. But the performances will be good anyway.
Okay, we have another question from Ignatius of Wasco in St. Lucia, which asks, what about the effect of toxic chemicals such as ammonia, pesticides, etc., on the biological components of the wetlands?
Well, I would say, like for the question of oils and or hydrocarbons, is that in normal situation, we can find pesticides, ammonia, and so on. We have ammonia for sure, but we can find pesticides and so on. So there is no issue on that. The like other system we have with treatment wetland, it's a biological system like activity exclusion and the others. So in normal situation, there is no impact on the biological activity. But of course, if you expect to use the washing of agricultural machine where you use pesticides, you wash the tanks and you put it on the treatment wetland, the concentration will be more higher, and in that case you can have punctual effects that can affect the performances over a few days or even kill the plants, and that could be a problem. But it's very specific situation where you have very high concentration. Is not the classical pesticide concentration you can find in urban areas.
Jacqueline Miller says, you mentioned odor problems briefly. Is it a common issue or easy to control?
The smells?
Yeah, the smell.
Yeah. So what we want to implement in such system, it's mainly aerobic activity. That means that the treatment wetland itself will not produce smells, but you can have, in tropical climate, you can have smells that are produced into the sewer or can be produced into the batch feeding system, where we store water during 1-2 hours before to feed the treatment wetland system. And so as the temperature is high, 25-30 degrees, the production of smells can be high in the sewer and in this first tank. So in the sewer, there is no relation to the technology itself. It's true for every kind of technologies. For what can happen in the feeding batch system, in that case, the idea is to design the system with maybe different cells to avoid too long storage, and let's say less than 1 hour, to be sure that we will not have smells produced here. But what we observed is when we produce the smells in the sewer or in the tank, or both, on the treatment plant itself, the smells appear only when we batch the system, because we strip the gas from the water. And so it's a smell that is produced, let's say, 10 times a day, and that lasts 1 minute, no more. So 10 times a day, 1 minute in that case.
Virginie Clarimer asked, do you know examples of reuse of treated wastewater coming from the constructed wetland?
Yeah, mainly, well, in France, let's say that it's mainly for agricultural irrigation. And even the example I gave you in Martinique Island with the rum distillery factory, it's to irrigate banana trees. So it's mainly this, but there is a few examples in the world where we use the treated wastewater for toilet flushing, but in that case, there is a disinfection system at the end, or to produce, reuse. It's not domestic wastewater, but it's the water that coming from car washing that is treated by wetland system and reused for car washing. That there is example as well like this. So there is examples, yes, but main example are for agricultural irrigation.
Okay, next question from Fanny Pero. Where are we in the development of the wastewater treatment plant in the non-French islands of Cuba, Dominica, and St. Lucia?
So that's that's a question that the CARIBSAN project needs to face, to try to see what has been done in those islands. So I don't know if you have ideas on your islands. It's maybe a question for you, Ignatius.
Well, I think where we are now is the project is now rolling out, and we're in the initial phases. So, because as we indicated at the start, it's a very short window to complete the first phase of the project by next December. But what it's seeking to do is to begin to do a lot of the research and the training and building capacity in the areas. And there are some areas, we, as the project rolls out, and we will be liaising with the water utilities in Cuba, St. Lucia, and Dominica, as to some of the sites that they may consider for running the pilot. I think in St. Lucia, there is a particular example, I'm told, of a particular hotel that has such a system. And at some point when we will be doing the visits during the pilot, we would be able to have a visit of that facility, as well as the ones that are operating or operational in Martinique, as you know, things improve with travel.
What I can say about the development of the technology in the world is that the research on such system started 50 years ago in Europe, and there is now a lot of system in Europe working, and it became a natural technology for small communities. But as well in US, as well in Canada, and now it's become more and more applied in China and in some Asian country. And in South America, there is more and more research and activities around treatment wetlands, but the application is not as common as in Europe. But it's the activity is in terms of research and pilot application and demonstration in South America is growing fast.
Magnus Williams of Dominica, the Wasco, asks, can you comment on the observed treatment of effectiveness in tropical environments compared to your experience in France in a temperate region?
Yeah, what is really important, as Joseph presented, is that the development of the plants is quite fast and homogeneous, to be able to reach this mechanical effects that we are looking for, the mechanical effects related to the stem development that pass through the deposit layer and allow to maintain the permeability of this deposit layer. So that's something very important. A fast and homogeneous stem development, rhizomes, growing by rhizomes, to be able to follow the evolution of the sludge deposit. And it's, of course, local plants, not invasive, quite robust for the competition with other plants, and plants that will not store rainwater in the leaves to avoid mosquitoes development. So it's mainly that. So that's something anyway we need to, in the CARIBSAN project, that we need to work on it with the local experts in each island. So we will we first ask for the partners the contact point for the local experts in terms of plants, of tropical plants. And then we will discuss with them with a list of different characteristics of the plants that we are looking for. to try to select and to see if there is a local new plant that we never studied that could be interesting to test.
Okay, we have, good to see Susanna Scott is on the webinar with us. Welcome. Her question is, what about the land requirements, including size requirements per user?
Okay. So what in tropical climate, what we observed is that what is the design we used, we are between 0.8 and let's say 1.5 square meter of filter itself. That means we need some additional area because we need to be able to operate the filter. So we need place in between. And so we can go until from 2 to 2.5 square meter per PE, according to the design and the performances, the outlet performances you want. The other possibility is to go to a more intensified system with forced aeration, but it has not been tested yet in tropical climate. And in that case, we can stay below 1 square meter per PE with only one stage. And so the total footprint will maybe reach 1.2, 1.5 square meter per PE.
Okay, next question from Ivanira da Costa James of the Wasco in Dominica. She's asking about this, how does the soil type affect the wetlands and which process is used for selection of the wetlands or the site or siting a wetland?
Yeah. So for the soil, I want to precise, like it has been showed in the presentation, that we do not use natural soil. We use sand, gravel, pea gravel, but it's never soil because of the clogging risk. So this material we use, we try to work without sand because it's a good sand is sometimes hard to find. But what is important is that this material is quite clean with not too much fines in it, and as well that can stay stable with time. That means that will not suffer from during the implementation from abrasions and so on. And after, it can be sand from, it can be spherical or not, it doesn't matter, but we need to measure the permeability of the and the porosity of the material to be able to select a good one. And after the selection of the size, the particle size, it will depend on at which stage we are. It's always a compromise between performances and the lifespan of the system. Because if you use a fine material at the first stage, for example, you will have a really good filtration, but no air, no oxygen transfer, and so you will clog your system quite easily. And so it's always a compromise, and we adapt the particle size of the system according to the stage of treatment, so to the quality of the influence and to the quality, the target quality at the outlet.
All right. Yeah, and the questions are coming fast and furious in the chat. We have Magnus Williams again. Apart from tolerance to anoxic and water stress, what are some of the properties of the suitable plant species in the Caribbean which make them effective for constructed wetland use?
I spoke about the mechanical effect, which is important. I spoke about to not retain rainwater in the leaves for the mosquitoes. I would say that despite the water stress and the anoxic stress in tropical area, it's a competition with other plants that can come from outside of the filters. And it's something we observed in not in Martinique and Guadeloupe Island, but we observed in French Guiana, that the plant from outside can easily go inside the filter. And so there is a huge competition between the plant we want to grow and the invasive plants. And so that means that we need a plant. If we do not want to clean and remove the invasive species too often, which is hard task during the first year, then we need to choose a plant that will grow quickly and fastly. Yeah.
There's a question from Gary Pilgrim. Has any studies been done on vegetation grown within this system to be used as feedstock that may be consumed by ruminant animals?
Yeah, that's a very interesting question. That's something that has been studied mainly in Africa. But in the study we did in the French island, not, because there is still the issue about the plant that was in contact with wastewater, and so what is the possible transfer to the animals in terms of pathogen transmission. And so it's not allowed in France. It's not really necessary, maybe, in the French context, but in other contexts, like in Africa, where there is some issue with the water resource, that's things that has been studied effectively to promote growth of plants that can be used for feedstocks. So that's, if it's interesting for your territories, that's something that we can look for. But we have, in that case, we will have as well to see how to control the pathogen transmission risk.
Okay. From Fanny Pero, where are we? Oh, sorry. Where are we in the development of individual wastewater treatment plants less than 20 PE? When will this system be authorized for individual treatment under 20 PE?
Well, I think it's very specific to the French context, this question, isn't it? I don't know. So. Because yeah, in France and let's say in Europe, systems that has to be applied below 20 P has to comply with a platform test and to have an agreement. And so there is agreements in Europe for treated wetland systems that are designed for temperate climate and not for tropical climates. And so we did a study about the application of treatment wetland with tropical design in tropical climates. And so it was to show that the system works perfectly below 20 P with the design I presented you. But now the question is how the French government will agree to have an authorization of this new design without passing through a dedicated platform test. So I think it's really specific to France, this question. So there is discussion running actually with the government, and so I'm quite confident that we will be able to find a good way to allow it, because anyway the results are there, it's working perfectly. So. But after, I don't know on your country how it is, how the regulation allow or not which system for on-site sanitation. If there is a specific regulation for that.
Right. From Hippolyte Austri of Dawasco in Dominica. In a small housing complex that hosts about 300 persons, is daily maintenance required? If so, what sort of activities are required and how many workers are needed to maintain this type of system?
So it is not a daily maintenance. Like Joseph presented, it's 2 times a week visit on the system. The minimum is to make the alternation and have a look on the functioning of the system. So it can be only 10 minutes, and that's all. And so that's 2 times a week, and on a lower frequency, there is other things that have to be done, like cleaning the pumping or the dosing batch system, let's say once a month, and removing the weeds during the first year, it's once a month, and once a year cutting and removing the plants. So it's quite simple, but it's not every day. And when it's 2 times a week, it could be only 5-10 minutes. It's quite easily, and it doesn't require any specific technical competencies. I expect, well, let's say, being well introduced to the technology and what are the important key points to follow.
Okay. Chantal Gaston from WASCO. Since we are from different countries looking forward for the implementation of constructed wetlands, have an assessment study been done that is in terms of permeability of the soil type for the application of the type of plant to use? I think somebody answered that in the chat. Yes.
Yeah, what I say is that we do not use soil, but we need to see in each country which kind of material we can find. And because according to this to the type of material we can find, we will have different maybe technologies that will be able or not able to implement. And so that's why there is as well questionnaires that will be sent to the partners soon, and on which we ask for the different material we can find on each island. And for the part of performances, yes, Fanny say that's another step for the. No, what are the next steps for the CARIBSAN project? Well, let's say it's making demonstration and a demonstration system to be able to have performances that each country can show to all the stakeholders. And yep, mainly that.
Yeah, I think that's the. Oh, you see the other one, the last one. Yeah.
The cost, yes.
Cost.
That's the big question. So until now, it's not possible for me to answer the cost question for each country, of course, because the cost will depend on the price of the material, of which design we do, on the cost of the man-work, and that can be different from a country to another one. So what I can say is that if we compare the investment cost for each technologies, the smaller is the treatment plant capacity, the higher is the cost per habitant. For each technology is the same. In France, in mainland France, what we observe is that the treatment wetland system is cheaper per people equivalent than activated sludge system in terms of investment cost until 2000p. And then activated sludge start to be more interesting in terms of cost, investment cost. If we take into account the operation the cost for operation over 20 years of operation. In that case, the cost being 5 times, the operational cost being 5 times higher for activated sludge than treatment system. The point where the two curves cross each other moved to 2000 to almost 5000 P in France mainland. But this point where the two curves cross can change from one context to another one. And we observed that, for example, in the French island, where many electronical mechanical system come from France, so there is a high price because of the transport. So this crossing point between the two curves move to higher capacity. So that's something we need to try to evaluate for each country. But when I told you that the biggest treatment plant for domestic wastewater was of 25,000 P, it is in Moldova, in Europe. And they compare, for these capacities, they compare locally the price with activated sludge. And treatment wetland was cheaper for 25,000 P. So you can see that it's very specific to a country. So that's something that we need to address in the CARIBSAN project.
Yes, and I think that I myself would have asked, I know in some of the aerated treatment systems, they would use aquatic animals like fish and so on, so as a control mechanism. Is that applicable in a constructed wetland to use some species of fish?
To control the quality at the outlet?
Well, not necessarily the quality, but to know, to have ideas of the, whether the quality of the water. Yes. Yeah.
Yeah.
Or is it feasible at all for any reason?
Well, for some fishes, I knew this system for potable water mainly, but do you use it for the outlet of activated sludge?
I don't know. I was just asking, since it's.
But it shows that anyway, there is for fishes. I don't know, but there is some what we call bioindicators that are developed to address some specific toxicity on rivers or for the outlet of treatment system. So there is, but they are usually dedicated to specific toxicity, not all. So sometimes you need to apply different bioindicators to follow the full screen of possible pollutants.
Okay. Okay, that seems to be the end of the questions that we have in the chat. I think, oh, I missed something here. Is the PE, is the unit population equivalent used in the Caribbean islands for CAWASA or others? I don't know that. I don't know if somebody who is more technical than I am can answer this. And there is a last one about methane production and other gases from constructed wetlands.
So as I said, we promote systems that work in aerobic condition or just anoxic if we want to reach denitrification, but never anaerobic. So when it's well designed and well operated, there is no methane production. But if the design is not good and that you clog your system, I will say maybe not methane production, but you can have some smell. But that's why we design the system to avoid any anaerobic condition. That's really important.
Okay, I think we have done very well within the time frame. I don't know if there are any other comments or questions? Camille, over to you at this stage.
Thank you very much for all the participation and all the questions and for the nice presentation. I think it was really interesting and I hope useful for Caribbean actors. So from my side, I think it's okay just to say thank you. Thanks a lot to you, Ignatius, for the organization of this first webinar in collaboration with CARIBSAN. And thank you to Joseph, Pascal, and all the participants for their active questions. And maybe just one thing to mention is that we will send you a satisfactory survey in the following days. So it will be very helpful for us if you can reply to this small survey. It don't require a lot of time. It's just to help us to determine the next topic of our next webinar. If you want to deepen on operation and maintenance or on conception or sizing of treatment wetlands, for example. So this survey is for you to indicate the topics that interest you the most and that you would like to be covered for the next webinar. And maybe also for the countries which are not for the moment part of CARIBSAN project, if there would be an interest for deploying treatment wetlands on their territory, and if yes, what they would need. So this satisfactory survey will help us to determine our next activities. So thank you for answering it. It's just like 5 minutes. Thanks a lot.
Well, let me thank again all the very interesting and educational presentations by Pascal and Joseph, and for the support of the International Water Office and all the other participants from the water utilities in the Caribbean who joined us this morning. Seems that the morning has turned out to be very good in terms of participation. The questions were on point and very technical as well. So that's a good step. And we would like to, again, wish everyone a safe, to keep safe and well. And as we are getting into the festive season, we want to wish you and your families a very joyous holiday season. And let's see you next year in one piece and to continue the work that we have started. Thank you very much. This is Ignatius, Executive Director at CAWASA, signing off. Have a wonderful day all. I will be sending this survey later today, as well as the recording of the webinar for those who missed it. Thank you very much.
Thank you.
Bye.
Thank you. Goodbye.
Bye-bye.
Have a good day.
Bye-bye.
Thank you very much.